Okay, in this section, we discuss a very useful concept, the distance from a point to a set. Here, suppose X is a point in Rn, and A is a subset of Rn. Then we can define this number denoted by dA of X, which is the infiniment of the distance from X to Y. Y runs through the set A. Okay, we have this number dAx. This is called the distance from X to the set A. From X to A. Okay, geometrically, here is the set A, and our X is here. Then, for every Y in A, we have the distance from X to Y, which is the length of this segment, or the norm of X minus Y. So for different Y, this distance is different, but the infiniment is the least distance from X to A, if it can achieve. Okay, so this is a very intuitive concept. I remind you to know that there might not exist, not necessarily exist. It is not true that there always exists Y belongs to A such that this distance is the distance from X to Y. Such a Y might not exist, might exist or might not. So this is the concept. Okay. Now, when X take different X, we can compute the distance from X to A by this definition, and therefore we have a function. This distance defines a new function. The function which is dA defined on Rn, real valued function. For any X in Rn, the value of this function at X is the distance from X to A. We just defined. Okay, so take different X, we can have different distance. Therefore, define a new function dA. So this dA, this function is very useful. From the calculus point of view, the first thing we are interested in is that whether this function is continuous. Actually, this function has very good properties. We will solve that. For any xy in Rn, this function the absolute value of the function at these 2 points will not greater than the distance from X to Y. Okay, this means this function is Lipschitz continuous. Which this Lipschitz constant 1. Okay, so this is very useful inequality, which implies that dA is uniformly continuous. Of course, it is continuous over all of Rn. So how to prove this? The proof is not difficult. We prove this result. Okay, so for any A in the set A, we have x minus A x minus A, the norm of x minus A by the triangle inequality will not greater than x minus y plus y minus A. This is true for every A, okay? And but we note that the left hand side, by the definition of the dA, we have the left hand side will not greater than will not less than dAx, okay? Because dAx is the infiniment of this distance when A change over the set A, okay? So we have this inequality. We forgot the middle term here. That is dAx will not greater than x minus y plus y minus A. But this is also true for every A in the set A. Therefore, take infiniment on both sides. The left hand side does not depend on A, so it remains unchanged. While the right hand side will not. The right hand side will become the infiniment of the distance from y to A. Therefore, it is the left hand side unchanged. The right hand side, the first term does not depend on A, therefore it's also unchanged. But the second term, when A change and take an infiniment, it will become dA of y. dA of y. Okay. So from this we see that dAx minus dAy will not greater than the distance from x to y. So interjecting the role of x and y, we see that the dAy minus dAx also less than the norm of x minus y. So we can take absolute value to get the result we want. So this our inequality is proved. Okay. So this trick is very useful. You fix an A and then take an infiniment when A changed. Okay. And also from the definition of dAx here, the definition of dAx, we see that if x belongs to A, then of course dAx is 0. But I remind you that even if x is not in A, it might happen that dAx is also 0. Okay, this is also possible. Okay, this is also possible. For example, if x is here on the boundary of A, okay, so but this point is not belongs to A. This is also possible. A concrete example. Example of x not in A but dAx is 0. We have many examples. For example, A is the unit ball, okay, and the norm of x is 1. What's this? So A is a new unit ball. The boundary of the ball is not contained in A, and the norm of x is 1 means the x is here, and this ball is A. So the distance from x to A is 0, as you can check. But x is not a point in A. Okay, so you need to notice this example. And another important result I will want you to know is that if A is closed, as I said before, it is not necessarily has exist a point in A such that the distance from x to y is dAx. Okay, this might not be true. But if the set A is closed, then this is true. This is what I want to remind you. If A is closed, then there exists a point such that the distance from x to this point is exactly the distance from x to the set A. Okay. So to prove this, it is also not difficult. Because dAx is the infiniment when y valid in A, the distance. Therefore, by the definition and by the property of the infiniment, we can find a sequence. How to find a sequence? So, for any integer k, by the definition or property of infiniment, okay, there exists a point, say xk in A, such that xk, the distance from xk to x, of course this will not less than dAx, but this will not greater than the infiniment plus 1 over k, because the infiniment is the largest lower bound. Increase a little, it is not a lower bound anymore. Therefore, the set where we take infiniment will contain an element less than this number, because this number is not a lower bound. So for every k, we can take an xk here. This implies that the distance from xk to x converge to dAx. So this is a sequence of convergent real numbers. Okay, a sequence of convergent real numbers. It must be bounded. So there exists an R positive such that every element in this sequence is not greater than R. So in particular, xk will not greater than by the triangle inequality. No. Okay, so this will not greater than R plus X. So the sequence xk is bounded. This is important. Xk is bounded. So it has a convergent subsequence. A subsequence. xki converge to some point A. But our sequence xk is taken from the set A. So the subsequence xki is also a sequence contained in A, and it converges. But A is closed. This is our assumption. So A must contain in A. Okay? And the distance from X to A, which is the limit I goes to infinity, xki minus A. Okay? We know this is true. But at the very beginning of this page, we know that the right-hand side, the distance from xk to x converge to dax. And here, xki minus A, the norm of xki minus A, is a subsequence of this convergent sequence of real numbers. So this must be the same limit, must have the same limit. So we find a point small a belongs to the set capital A, so that the distance from x to this small a is exactly the distance from x to the set A. Okay, this proves our result. Okay.